In this video, we're going to return to the idea of stoichiometry and incorporate what we've learned about the ideal gas law and predicting things like moles of a gas into stoichiometry problems that have gases in the chemical reaction. So we've already looked at stoichiometry problems that are mass to mass conversions, and we've looked at stoichiometry problems that also involve using concentration or solutions. And now we're going to incorporate gases. And so at the heart, at the very heart of stoichiometry problems, what we have is the mole to mole conversion. And that's the essential part that is the same in all of these different variants on a stoichiometry problem. And that's the piece that just does not change, honestly. Um, and so this is at the core, but we can get to that mole to mole conversion in a lot of different ways. And so this is all about predicting how much of something will form or will be consumed within a chemical reaction when you know something about something else. And so we can get to moles either from mass using molar mass. We can do that from a solution, so from concentration, um, or we could do it from volume. So like molarity. And now we're going to be able to do it using the ideal gas law as well. And so we can get to that number of moles for one compound in three different ways, and we can convert it then into the moles of a different compound within the chemical reaction. And then coming from that point, when we know the moles of something, we can still convert that into mass or into concentration or volume or into another property of a gas or like volume or pressure. And so that's kind of so we'll look at the gas component, but I think it's important to know that we can go from the mass of something and predict the pressure of a product. Or we can do any combination of these three kind of ways of tackling this problem. And when you're in the chemistry lab, or if you're doing research or you're out doing research in a different field, like this is kind of this is something that'll come up again. And this is actually a usable piece of information, and one that as a problem solving strategy can be really flexible. So let's talk about this. So when we focus on just the gas stoichiometry component, we're going to see that the multiple conversions between reactants or products will be the same as any stoichiometry problem that you use mass or solution information. Um, and here's that kind of core piece we were just talking about right here. But what we'll do with these gas stoichiometry problems is use Puvnert, or the ideal gas law, to calculate the number of moles of a gas, to then allow us to do that mole to mole conversion. So rearranging our ideal gas law, I think especially for these gas stoichiometry problems, it's important to remember the version that has n number of moles just isolated on one side. And we can use that. I think the best way to learn this is to walk through an example and then to try it on your own. So let's go ahead and do that. Let's do an example problem, and then we'll have a practice problem that you can try, and I'll have the solutions too. So sorry, I had to modify my chemical formula because I didn't have all the stuff. The water was tied up in being aqueous, and I forgot to put it on the product side. So we are going to look at the decomposition of hydrogen peroxide into oxygen and water. Magnesium oxide catalyzes this reaction. It happens on its own, but it happens very slowly. Magnesium oxide will make it happen quickly. Now, a catalyst will participate in the reaction but reform itself. So it's not part of the stoichiometry of the problem. It'll get reused and reused and reused and reused and reformed and reformed and reformed. So the reaction is going to be carried out in a flask attached to a balloon so we can catch any gas that's produced. We've got some information in here. It tells us that we have a temperature of 298 Kelvin that the experiment will be conducted under. There's a pressure of 1.002 atmospheres. And what we're interested in is that volume of oxygen gas that's produced when we have 1 gram of hydrogen peroxide that is going to react with water in the catalyst and just decompose. So to solve this problem, then we are going to use we're gonna use that mole to mole conversion going in between our hydrogen peroxide and our oxygen. So the first step is to figure out the number of moles of hydrogen peroxide that we have, and we're given this 1.0 grams And so I'm going to convert this into moles using molar mass. Now this is going from mass to moles. This is something we've done before. Hopefully it's familiar. We'll need the molar mass from the periodic table, which is 34.014 grams. All right, so dividing that one by that molar mass, we're going to get a number of moles of hydrogen peroxide. That's 0.02939997. I'm keeping all the digits. So now with this information, we can do our mole to mole conversion, which will take us from our hydrogen peroxide to our oxygen. And so we have a 2 coefficient and a 1 coefficient. So we have a 2-to-1 ratio. So I'm going to take those moles of hydrogen peroxide. I'm going to convert it into moles of oxygen using my coefficients as my conversion factor. And that's going to give me 0.0146998 moles. All right, so now I have moles of oxygen. That's great. And I really need to figure out the volume of oxygen gas that I am going to produce. So I kind of have a sense of how big that balloon is going to get. So I'm going to use the ideal gas law now. So this is us using the gas part of gas stoichiometry. So I have the ideal gas law, and I'm solving for volume. So I'm going to rearrange this. So I'm going to plug in. Now, the moles that I'm going to plug in here are the moles that I just calculated of oxygen. So that's going to be our 0.0146998. I have my temperature in Kelvin. I have my pressure in atmosphere. So I'm going to use my 0.0821 liters times atmospheres moles Kelvin, and my temperature of 298 Kelvin, all divided by the pressure in the room, which is going to be 1.002. All right, then I'm just plugging that into my calculator at this point. Give myself a little bit more room here. And when I do that, I'm going to calculate a volume. I'll put it over here. That's equal to 0.359 liters. Right here. So we can use stoichiometry, so we can use that problem solving strategy with these ideal gas law problems. All right, now the next video has the solutions to a practice problem. Give it a try first.